Hello all, good evening. Welcome back to my YouTube channel all about VLSI. Hope you're all doing good. I think my voice is audible and my screen is also visible, right? So let us start today's session. So before going to start today's session, please make sure that you have subscribed to our YouTube channel all about VLSI. Okay? Yes. So let's start with our session today. So today we are going to discuss about diode limiters. So it is also a application of our diodes. So we are going to discuss about diode limiters. So let us see what are these diode limiters and how they are being used. Okay. So I will write the title here. So let me change the pointer color also. Yes. Diode limiters. So what are these diode limiters? Okay. So why these diode limiters are used? What are these diode limiters? Let us now try to understand. Okay. So diode limiters are also called as clippers. Diode limiters are also known as clipper circuits. So these are also known as clipper circuits. What are meant by these clipper circuits? Basically, diode limiters or the clipper circuits are used for limiting or clipping the positive part of the input voltage or the negative part of the input voltage. For example, if we have a input waveform AC voltage like this, so let's say this is our input AC voltage, sinusoidal wave input AC voltage. Okay, so if we pass through this diode clipper circuit, then the output of this positive clipper circuit, let's say this is a positive clipper circuit, then the output of this particular positive clipper circuit will look like this, so only a small part of the input will be a positive input will be passed and remaining part will be clipped off. So if the output, you can clearly observe the positive part of the input is being clipped off. Okay, the positive part of the positive part of the input has been clipped off, but the negative part remains the same. So this is a positive clipper. So basically a positive clipper will limit or clips the positive part of the input voltage if it is a positive clipper. And for a negative clipper, let's see a negative clipper also. So let's say this is our input of the negative clipper, and the output of negative clipper will look like this. The input part will be unaltered and the output part will be clipped off like this. The output part will be clipped off. Here the negative part, if you observe, the negative part has been limited or it is clipped off. The negative part has been clipped off or limited, whereas the positive part remains as it is. So it is a negative clipper. So this operation is performed by a negative clipper or negative limiter. Okay, so this is the operation of a positive clipper and a negative clipper circuit. So a positive clipper circuit will clip off the positive part of the input, that is, it will look like this. The positive part of the input waveform will be clipped off, and in the negative clipper, the negative part will be clipped off. Okay. Now, why we need this clipper circuits? Why we need this? Let's say this is our digital circuit. And on the left hand side, we have our inputs. On the left hand side, we have all our inputs. And on the right hand side, we have our outputs. So I'm saying it is a digital circuit. So this digital circuit will contains all the digital components like ICs, okay, op amps, or we have some digital components. All we have in this particular digital circuit, we have inputs, outputs, and it consists of some ICs, op amps, all the digital components we have in this digital circuit. We already know that digital circuit, so digital circuits need only small voltages. Digital circuits need only small voltages of range 0.5 volts to some in the 2 volts. Like say the input voltage or the voltage or the power supply will be a very small amount. Okay, but what if we supply, but what happens in the real life, our voltage will be very large. Okay, like it will be around 15 volts to 20 volts, etc. The power supply, it will be so large, but we cannot give this huge amount of power supply to our digital circuits. Okay, so to cut off the input power supply voltage, like we can cut off the 15 volts to around 2 volts or 1 volts. Okay, to perform this operation, to cutting off this voltage, or to reducing the voltage from 15 volts to 1 volt or 2 volts, this operation is called clipping. This operation is called clipping. Basically, we perform this operation, and after clipping the particular voltage, we apply it to our digital circuit. So that is why we are going to use this diode clippers or diode limiters. Okay, so let's see a circuit, how a positive diode clipper look like. Let's see it. Positive diode clipper. So let me draw the diagram for a positive diode clipper. So here we have a voltage source, and let's say this is resistance R1, and this is our diode. Okay, it is connected to ground like this, and here we have the load resistance RL. So across this load resistance, we will get the output. Okay, across this load resistance, we are going to get the output. So at the left hand side, we have the input power supply and the diode and the load resistance, which is connected parallel with the particular diode. Okay, and the input voltage is AC input voltage. I will draw the waveform here. So this is the input voltage which has been applied to our power supply or our diode. Okay, this is resistance R1, RL and the diode. Now, if you observe, the diode is in forward bias condition. When it is forward bias condition, when there is a positive input, when there is a positive phase of the input, for positive phase of the input, the diode will be in forward bias. Why? You are applying positive, okay, positive to anode and negative to cathode, so it will act as forward bias. And for negative half cycle of the input, it works as a reverse bias. I will write it here. For positive phase of input, for positive phase of input, the diode work as a forward bias condition. The diode will be in forward bias condition. Whereas for negative phase of input, the diode will be in reverse bias condition. The diode will be in reverse bias condition. Okay, so for for positive phase of the input, the diode will be in forward bias condition, and for negative phase of the input, the diode will be in reverse bias. For negative phase, if you observe here, if we are applying the negative phase, the negative voltage is being applied to anode and the positive is being applied to cathode, so it will be in reverse bias condition. Okay, so if you observe, for the positive phase of the input, the diode will be in forward bias condition, whereas the negative phase of the input, the diode will be acting as a reverse bias condition. What happens if it is in forward bias, that is in the positive half of the input? Then the diode will act as a voltage source. Okay, we have seen the approximation model of this particular diode, right? The approximation model, the second type practical model. So when it is in forward bias, okay, I will write it here. When the input voltage is greater than zero point 0.7 volts. We are correct. We are considering this particular diode as a practical diode. About the practical diode approximation models, all we have discussed in our previous sessions. If you haven't watched them, please go back and rewatch them. What are the diode approximation models? Everything we have discussed in detail. Okay. So here we are considering the diode to be our practical diode model. So what happens? We will replace this with a voltage source when it is being in forward bias. So it is being replaced as a voltage source. Now, if the input voltage is greater than 0.7 volts, then what happened? So this particular diode is being replaced by a voltage source of 0.7 volts. A voltage source of 0.7 volts. So at this point A, if we observe at this point A, what is the voltage? You are having 0.7 volts and this is connected to ground. So this instead of this diode, if it is in forward bias, here we will get a voltage source of 0.7 volts and here we have a load resistance RL. So since the voltage source and the resistance are in parallel, so the voltage across the resistance RL will be equal to 0.7 volts. The voltage across this load resistance will be equal to 0.7 volts. Okay, and after applying the input greater than 0.7 volts, the voltage across this resistance will remain 0.7 volts only. It will not change. It will be constant. Okay. So let's say if your input is equal to 0.7 volts, then voltage across RL will be equal to 0.7 volts only. And if input is greater than 0.7 also, the voltage across load resistance RL will be 0.7 volts only. If you go on increasing the input voltage, there will be no change in the output voltage. Okay, why? Because we have considered this diode as a voltage source. Okay, because we have considered this as a voltage source. I will draw it here for your clear understanding. So when we have approximated our diode, so this is R1. So when we have approximated our diode model, so it will act as a voltage source of 0.7 volts when the diode is in forward bias condition. This is RL. So this is of 0.7 volts. Okay. So this is 0.7 volts. Here you having 0.7 volts. Then at the resistance RL, the output, the voltage is 0.7 volts only. So how much you increase the input voltage? Okay. I will draw the waveform also. Okay. For the positive phase, let's say here somewhere you are having 0.7 volts. After this 0.7 volts, how much you go to the peak voltage also. If you reach the peak voltage also, let's say it is around 10 volts. So if you apply 10 volts input also, the output will be equal to, I'll draw the output. So this is the input and the output after 0.7 volts will remain at 0.7 volts only. How much you give the input, how much the input is given, okay, after the 0.7 volts, it will remain at 0.7 volts only. Okay, because it is approximated as a voltage source. The diode is approximated as a voltage source and it is since parallel to the RL. So here we are going to check the output voltage. So here the output voltage will be equal to 0.7 volts only. So in this diagram, you can clearly observe that positive half cycle has been clipped and it is been restricted to 0.7 voltage and it has been restricted to 0.7 voltage. So this is how the positive clipping is happening in the case of our diode. Here positive clipper circuit. Okay, so this is how the positive clipping process has been happening. Now if we observe the negative half cycle of the input, let's say this is our negative half cycle of the input, then what happens? If negative half cycle has been applied, let's see the circuit, then what happens? The diode will be in reverse bias condition. When we apply the negative phase of the input, then what happens? We have already seen the diode will be in reverse bias condition. What happens if diode is in reverse bias condition? We have already seen in our diode approximation model. Will act as an open circuit. We have already seen this in diode approximation models. Then what happened here? Diode will be in open circuit condition. Then what happens if it is an open circuit? I will redraw the diagram again so that it will be easy to analyze. This is our voltage source and this is our R1 and here the diode will be in open circuit condition because it is being reverse bias. Okay, open circuit, and here we will get RL. This is RL. Okay, so this is our input voltage source. Input voltage source. And now it is that we are giving negative phase. We are giving negative phase, not positive phase. Negative phase. That's why we are getting open circuit condition of the diode. And this, now what happens if this particular diode becomes open circuit? What happens? Then this R1 resistor and R2 resistor will be in series. R1 and R2 resistor will be in series. Okay. What happens if R1 and R1 and RL are in series? The voltage will get divided. The voltage will get divided between R1 and RL. Okay. So how to find out the output voltage? Vout. Vout can be found out by RL divided by R1 plus RL into Vin. So this is how we are going to find out the output voltage, Vout. This is the magnitude of the output voltage. So this is the magnitude. And what is the sign of this magnitude? Which is nothing but minus. Why? Because we are applying negative voltage, so the sign becomes minus. So whatever the result we will keep minus sign before the magnitude. So this is how we are going to find out the output voltage of a diode, output voltage of this particular circuit. Okay, so this is, so we are getting some magnitude. Okay, so if you see this magnitude, if you are applying this negative input phase, then the output remains as it is, or it may be decreasing value of the resistance RL, R1 and RL. Okay, so if you see the input negative phase is remaining the same, but the input has been clipped off. Okay, so this is how a positive clipper circuit works. This is how a positive clipper circuit works. So in this particular scenario, if we take R1 is small compared to RL. So if we consider R1 is very small than RL, then what happens? This R1 plus RL will become RL. This term becomes RL, and we will get RL divided by RL. So it will cancel out. So what we will have finally? Vout equal to Vin. Okay, so the waveform we are getting, so the input negative phase will be the magnitude of output negative phase will be equal to input negative phase. Okay, so why we are considering R1 is very less than RL. Okay, so this is how we a positive clipper circuit works. This is how a positive clipper circuit works. I hope up to here it is clear, right? Now let's see a negative clipper circuit, how a negative clipper circuit works. So what happens in a negative clipper circuit? In positive clipper circuit, what we have seen, the positive part was being clipped off and negative parts remains the same. Whereas in the negative clipper circuit, the negative input phase will be clipped off and the positive part remains the same. Okay, so let's see the circuit first and let's analyze the waveform. Okay, so this is our voltage source, plus minus, and let's say this is our resistance R1, and this is our diode. Okay, let's change the direction of this diode. Okay, it is connected to ground, and here we have the load resistance RL. Like this we have the circuit. So it is a negative clipper circuit. What happens for the input positive phase? I will draw it here. So this is my input AC voltage. So for input positive phase, tell me whether the diode is in forward bias or reverse bias. So from the circuit we can observe, if the input is positive, what happens if the input is positive? Then here, what happens if we get the positive phase? Here we will get plus and here we will get minus. So plus is given to cathode and minus is given to anode. So the diode will be in reverse bias. So the diode will be in reverse bias condition. The diode will be in reverse bias condition. So if the diode is in reverse bias condition, it is approximated to a open circuit condition. The diode is then approximated to a open circuit condition model. Okay. So what happens if it is in open circuit? Then the same R1 and the R1 and the RL will be series with each other. And the voltage, the input voltage will be distributed among the R1 and RL. And the output voltage at RL is given by this formula. Vout is equal to RL divided by R1 plus RL into V. I will write it here. So for input positive voltage, what is our Vout, which is given by RL divided by R1 plus RL into V input. Again, if we consider R1 is very less than RL, then R1 plus RL is approximately equal to RL. It is approximately equal to RL. Then RL will get cancelled and we will be left out with this term. Vout will be equal to Vin. Here we are applying positive input voltage. So if we apply for the positive input voltage, our output magnitude will be the same as the Vin. Okay. So this is how for a negative clipper circuit, when we apply a positive input phase, this is how it will behave. Okay. Now let's see what happens if we apply the negative input phase for this particular circuit. If we apply this negative input phase, then what happens? The diode will be in forward bias condition. The diode will be in forward bias condition. Why? Because here we are applying positive and here we are applying the negative. Okay. Now it will be in forward bias condition, but we are applying negative input voltage. Negative input voltage, that is after minus 0.7. So in the reverse bias condition, that is when input is greater than minus 0.7 volts, negative voltage we are applying. When the input voltage is greater than minus 0.7 volts, the diode will be in forward bias condition. The diode will be in forward bias condition. That is, it will act as a voltage source. That we have seen, right? So what happens if it is in forward bias condition? It will act as a voltage source. It will act as a voltage source. When the voltage across this resistance, output resistance RL will be equal to 0.7 volts. That is, it will be, the sign of this voltage will be minus. So it will be minus 0.7 volts. So here in the waveform, if you want to represent like this, you can represent. So at the output, for the input negative phase, at the output you will get only minus 0.7 volts, a constant voltage you will get. So if you observe the diagram, you can clearly observe that the negative input phase has been clipped off, whereas the positive input phase will remain the same, whereas the negative input phase will be clipped off. Okay, so this is the working of a negative clipper. So this is the working of positive clipper as well as negative clipper. If you want, I will give you one assignment. Try to find out what is our output, how the output look like. Okay, so let me draw the circuit and try to find how the output look like. Okay, so this is our input AC voltage. We have 10 kilo ohms and we have a diode connected like this with the ground. Okay, and the load resistance RL. Okay, and this is our input. Okay, 10 volts minus 10 volts, 10 and minus 10 volts. Peak to peak voltage is 10 volts. This is our input. Then find what is the output Vout. How Vout will look like. Okay, this you can try it out and you can post it in the comment section. Okay, so try this, you will get it clearly. Okay, yeah. So this is about positive clipper circuits and negative clipper circuits. Okay, now, so we also have one more type of circuits in this positive clippers and negative clippers only. So those are called bias limiters. What is actually happening in this particular positive clipper or negative clipper? If you observe in this positive clipper or negative clipper, if you observe, uh, in the case of positive clipper, if you clearly observe, the output voltage in the case of positive clipper is constrained to 0.7 volts. Okay, the output voltage of this positive clipper is constrained to only 0.7 volts. And in the negative clipper also, if you observe, our output voltage you are getting for the negative input phase, you are getting only 0.7 volts. What if you don't want zero point 0.7 volts, but if you want, let's say, greater than 0.7 volts? Okay, what if you want, if you don't want zero point 0.7 volts, you want greater than 0.7 volts? Okay, then what you can do, less than zero point 0.7 volts is not possible because barrier potential of this diode is zero point 0.7 volts. So less than that you cannot achieve. So greater than 0.7 volts only you can achieve. Okay, so in the normal positive clippers and negative clippers, 0.7 volts was the uh, 0.7 volts was the voltage you are getting. Okay, so how to get the voltage greater than this 0.7 volts? So you can use this bias limiters. So you can use this bias limiters. So let me draw the circuit for this bias limiters. So this is the circuit for a bias limiter. So this is how a bias limiter look like. So in this particular bias limiter, you are applying a voltage called bias voltage. So you are applying a voltage called bias voltage. So here you are applying a voltage called bias voltage with this particular diode. So what happens if you are applying? So let's see if you are applying our input voltage. The working is same. Okay, there is no difference in the working. If you observe, if you are applying this input voltage up to 0.7 volts, the diode will not be conducting, and after 0.7 volts for the input positive phase, then what happens? The diode will be conducting. The diode will be conducting, and here we will get a voltage. So that we will take the approximation of this diode to be of a voltage source of 0.7 volts, and here we will have this extra bias voltage. So if you observe this the circuit which we have discussed, yeah, here this circuit. So what happens for the input positive phase? We will consider this diode with our bias voltage V bias. So the output voltage in this case, it will be not equal to 0.7 volts, it will be equal to zero point 0.7 plus V bias. It will be equal to 0.7 plus V bias. So according to this bias voltage, you can adjust the output voltage. So if you want the output voltage to be around 1.4 volts, then you can apply this V bias equal to 0.7 volts. Okay, then the output will be equal to around 1.4 volts. So this is how you are going to adjust your output voltage. Instead of giving the output voltage stick to 0.7 volts, you can increase the output voltage. And in the negative clippers also, if you observe here, for the negative clippers, if you want to add the bias limiter, if you want it to behave like a bias limiter, you will add one more voltage source here. V bias. So at the output, you will not getting minus 0.7 volts, you will be getting minus zero point 0.7 minus V bias. That is, if you want minus 0.14, then you can keep V bias voltage to be equal to minus zero point 0.7. Then the total output voltage will be equal to minus 1.4 volts. So this is how you are going to control your output voltage accordingly to your requirement. Okay. Yeah. So this is about the input and output voltage of a clippers circuits. So this is how the positive clippers and negative clippers works. Okay. I hope you have got a clear idea about how a positive clipper and negative clipper works, right? Yeah. So that's all for this session. So if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you. Thank you for tuning in.